Welcome back, ladies and gentlemen, to Chapter 5 of our course on linear algebra in 2D. And in this video we're going to talk about the change of coordinates and how to compute it. Now, this is not going to be an easy one. There are not so many theorems in this video, but it will be heavy on computation and notation. So make sure to take notes and stop and rewind the video if necessary. And it really helps to follow the arguments closely step by step. And just as a warning, I think changes of coordinate systems can be quite confusing, so don't expect to get an intuitive grasp of it straight away. It will come over time with experience and repetition. Now, the first thing I'm going to talk about will be linear changes of coordinates, also known as change of basis. So expressing our vectors with respect to one basis and then changing it to the representation with respect to a different basis. Then I'm going to talk about affine changes of coordinate systems, where we can also choose a different origin, a different point as origin for our coordinate system. And finally, I'm going to show how a change of basis affects the representation by matrices of linear maps. So let's start with a change of basis. Now, why do we even need to consider such things? In practical applications, when we apply linear algebra to real-world problems, we choose a coordinate system somehow, and we do this to model the geometry of our problem. Now, in our setting here, we restrict ourselves to the two-dimensional plane, and a coordinate system is defined by a basis of the plane. So we pick two linearly independent vectors, and then we can express any other vector as a linear combination of those two. And the coefficients of this linear combination are the coordinates. This is what we saw in the previous chapter of this course. Now, a choice of such a basis, and hence a coordinate system, is usually guided by what I call convenience. So if you model your problem, there's some natural choice that appears natural for this problem and makes it convenient to express whatever you need to in the chosen basis. But yes, it might vary what is convenient for different tasks or different kinds of problems. So it's not always clear which coordinate system is the best. So you might want to switch between coordinate systems. And because of this, we must be able to somehow compute a change of coordinates from one coordinate system into the other. And as I said before, change of basis is a linear change of coordinates. So we use a linear transformation to change from one coordinate system to the other. And this amounts to using different axes and different length scales on these axes as reference points, or as reference for the points in the plane. Here I quickly recall this example we had in the previous chapter. Now, we had this vector v here, and we could express it in two different ways. In the blue basis, b1 and b2. So if we take 4 steps in direction b1, so we take 4 times b1, and then 1/3 a step along b2, then we arrive at our vector v. So 4 times b1 plus 1/3 b2 is the vector v. So the coordinates here would be 4 and 1/3. And we have the second basis b tilde, and if we go twice in the direction of b1 tilde and then add 1 times b2 tilde, so this vector here added to 2 times b1 tilde, we get v again. So the coordinates in the b tilde coordinate system would be 2 and 1. And this I can also write as a vector. So if I'm given any basis b with two vectors b1, b2, then the basis representation of a vector v in this basis, which are denoted by row b, row index b of v, is simply the vector which contains the two coefficients from this linear combination. So recall, because B is a basis, I can express V as a unique linear combination, lambda 1 B1 plus lambda 2 B2. And if I take these two coefficients and write them into a vector, then I call this the basis representation of V in the basis B. Yeah, and I'll use the Greek letter rho for this representation map. And as I said, these coordinates are uniquely defined for any vector v, so this is indeed a well-defined map. Now we have lemma 1, which states that for a given basis b, this coordinate representation is in fact an invertible linear map of the plane. So it's rho b is linear in its argument v, and we can invert it. We can find an inverse map. Now, suppose for the proof that v is this linear combination lambda 1 b1 plus lambda 2 b2, and the second vector w is mu1 b1 plus mu2 b2, and alpha is any scalar. Now we want to show that rho b is linear, so first we look at a multiple of v, so alpha times v. If we use this unique linear combination for v, is the same as alpha lambda 1 b1 plus alpha lambda 2 b2. So rho b of alpha v is by definition the vector with entries alpha lambda 1, alpha lambda 2, but then we can just take out this factor alpha and we get alpha times the vector lambda 1, lambda 2, and that's the same as alpha times rho b of v. So we can indeed take out the factor alpha from the representation map. And very similar, we can show that rho b respects the addition of two vectors, so v plus w. If we plug in the basis, the linear combinations in the basis b for v and w, we get this sum here. Then we can rearrange the terms a little bit, so we get lambda 1 plus mu1 b1 plus lambda 2 mu2 b2. And from this it follows that the representation in the basis b of v plus w is lambda 1 plus mu1 in the first row and lambda 2 plus mu2 in the second row. And of course we can write this as a sum of the two vectors lambda 1, lambda 2 plus mu1, mu2. And that's of course the same as the representation of v plus the representation of w in the basis b. So this means these two together mean that rho b is indeed a linear map, and rho b is invertible, since if we're given such a pair lambda 1, lambda 2, then we can simply compute v by taking this linear combination. So we can easily invert this map if we're given lambda 1 and lambda 2. We get our v back, the pre-image v, by simply computing lambda 1 b1 plus lambda 2 b2. And this shows that rho b is indeed an invertible linear map in the plane. Now, let's look at some examples. So here we have the canonical basis with the canonical basis vectors e1, e2. And for those, the basis representation is trivial, by which I mean rho s, the representation map, is just the identity. And that's easy to see. So if v is the vector alpha beta, then rho s of v is just, again, alpha beta, because by definition v is just alpha times the first canonical basis vector e1 plus beta times the second canonical basis vector e2. So applying this representation map to v doesn't change anything, and hence for the canonical basis it's just the identity. Here we have a second example, example 3, and this continues example 5 from chapter 4, and don't worry, I'll recall the details of that example in a moment. And what we had in this example we had the basis b and b tilde and the vector 4, 1. And we had the representation rho b of v to be 4, 1/3. So we saw that even in the picture I had in the beginning of this video. And rho b tilde of v is 2, 1. So as we computed, 4 times b1 plus 1/3 b2 is v, or 2 times b1 tilde plus 1 times b2 tilde is v. So this is why we have these representation in the respective bases for the vector v. Now these bases from that example were b1, b2, the vector 1, 0 and the vector 0, 3, and b1 tilde, b2 tilde, the vectors 1, 1 and 2, -1. Now we come to the question how to switch from one basis representation to another. And we first develop the ideas for that in this example. So suppose we have some vector v, and we know in the basis b it is represented by lambda mu. Okay? How do we get the corresponding representation for the basis b tilde? Now, to answer this, we use the fact that the basis vectors of the basis b, b1 and b2, can also both be represented as linear combinations of the basis vectors b tilde 1 and b tilde 2 of our second basis. So we do this, b1 is in fact 1/3 b1 tilde plus 1/3 b2 tilde, and b2 is 2 times b1 tilde minus b2 tilde. Now how do we find this? Either by taking a good look at the vectors and doing a little bit of guesswork, or by solving two linear systems to write b1 and b2 as linear combinations of b1 tilde and b2 tilde. And we already know how to do this, so we have done this in the examples in chapters 3 and 4, and later we will again see an example of this. So yeah, now we have expressed b1 and b2 as linear combinations of the vectors of the basis vectors from the second basis. And now we can substitute this into the representation of v as a linear combination of b1 and b2. So recall, we are given that v in the basis b is represented by lambda mu. So that means v is lambda times b1 plus mu times b2. And now to get v represented by b1 tilde and b2 tilde, we substitute these two expressions here for b1 and b2. So that gives lambda times this linear combination plus mu times this linear combination. And now we can rearrange the terms a little bit. So we have it as a linear combination of b1 tilde and b2 tilde. And what we get is 1/3 lambda plus 2 mu times b1 tilde plus 1/3 lambda minus mu times b2 tilde. Okay, so this is what we found. V is this linear combination in the basis b and this linear combination in the basis b tilde, where we used that we could express the b basis in the b tilde basis. So what this means is that rho b tilde of v, the representation of v in the basis b tilde, is the vector which has these two coefficients from the linear combination as its entries. So we're not quite done yet. We can rewrite this as the sum of two vectors, namely lambda times vector 1/3, 1/3 plus mu times vector 2 minus 1. And we see that this vector here is in fact just rho b tilde of the vector b1 from the first basis. And this vector here is just rho b tilde of the vector b2 from the first basis. Okay, recall that this was the linear combination that represents b1, 1/3, 1/3. and this was the linear combination that represents B2, so it's 2 minus 1. And this can be expressed as a matrix vector multiplication. So rho B tilde of V, this vector here, is this matrix 1/3, 1/3, 2 minus 1, multiplied by the vector whose coefficients are the representation of the vector V, but expressed in the basis B, so the vector lambda mu. If we multiply this, we get exactly this vector here. So we find that rho B tilde of V is this matrix here times rho B of V. Now, what we find is that the change of basis from B to B tilde is performed by multiplying with the matrix whose columns here are the representation of the old basis vectors B1, B2 in the new basis B1 tilde, B2 tilde, because the coefficients of the columns here were just taken from these two linear combinations. And it's also clear that the converse change of basis, so if we wanted to go from the rho B tilde V to rho B V, is performed by the inverse matrix. So we'll see that in more detail later. And the example we just studied contains all we need to derive a general method for changing representations in arbitrary basis. Now here we have a theorem 4 which describes the change of basis equation, and don't be scared of the notation that's coming up here. I know it's a lot of indices, but it's necessary to be precise here, and once you get used to it, it's actually quite convenient. So we're given two bases, B with vectors B1, B2 and B tilde with vectors B1 tilde, B2 tilde, and the following matrix M, B, B tilde, so upper index B, lower index B tilde, whose columns are rho B tilde B1 and rho B tilde B2. So the columns are the representation of the basis vectors from the first basis B in the second basis B tilde. And then for every vector V, the change of basis representation from B to B tilde is performed by multiplying this matrix here, this change of basis matrix, MB B tilde, by rho BV, by the representation of V in the first basis B. And what comes out is rho B tilde V, the representation of V in the second basis. And I choose the indices here, this notation I choose in the change of basis matrix, so that for every two factors in such an expression standing next to each other, every index that appears as a lower index and as an upper index must disappear in the end result. So they cancel out, and that makes it easier to remember which basis is going to be changed to what. So yeah, you see here on the left hand side we only have the index B tilde because we want the representation in that basis. So if we go in with rho B of V in the old basis, then this matrix here with the upper index B and lower index B tilde affects this change of basis, and you can think of it as these two indices cancelling out and only B tilde remains. So that's just a notation to make it easier to remember what we actually mean by these matrices. Now let's prove this. The proof is actually not very difficult. It's pretty much repeating what we did in the example before. So suppose V is represented uniquely in the basis B1, B2 as lambda B1 plus mu B2. And then we already know that these basis representation maps are linear. We've seen that in lemma 1. So we apply rho B tilde to V, so to this linear combination. So rho B tilde of V is rho B tilde of this. By linearity, this is lambda rho B tilde B1 plus mu rho B tilde B2. Yeah, and that's the same as multiplying the vector with entries lambda mu by the matrix which has these two vectors here as columns. So that's precisely the matrix we defined here. And the vector lambda mu is, because v is lambda b1 plus mu b2, is just rho bv, that is v represented in the basis b. And that proves our change of basis formula. Now the converse, I mentioned it before in the example, the converse change of basis going the other direction is just given by the inverse matrix. So if we have two bases b and b tilde, then the change of basis matrix m b tilde b, so taking the representation in the basis b tilde and giving you the representation in the basis b, is just the inverse matrix of mb b tilde, so the inverse of the matrix that does the change of basis in the other direction. And to prove this, we note that in the basis b, expressed in the basis b, the vectors b1 and b2 are just given by the two canonical basis vectors, okay? Because rho b of b1 is just 1 times b1 plus 0 times b2, so 1, 0. And rho b of b2 is 0 times b1 plus 1 times b2. And we get 0, 1. Now we apply theorem 4 twice. And we find the following. So if we multiply m b tilde b and mb b tilde with the vector 1, 0, then this is the same as multiplying it with rho b of b1. And by theorem 4, this is actually the same as rho b tilde of b1. And multiplying this with the change of basis from b tilde to b, we just get back rho b of b1, again by theorem 4. But as I just mentioned, this is just 1, 0. So we find the product of these two matrices multiplied by this vector gives the same vector. And in the same way, we can show that the product of these two matrices multiplied by the vector 0, 1 again gives the vector 0, 1. But what this means is we have shown that the product of these two matrices on a basis, on the basis 1, 0 and 0, 1, is the same, it does the same as the identity matrix does. So this matrix product and the identity matrix, recall that's the one that has just the entries 1 on the diagonal and 0 otherwise, they coincide on a basis and therefore they are identical. Okay, recall we have shown that linear maps that coincide on a basis must be identical, and of course that means matrices that when you multiply them with basis vectors and they coincide, then they also must be identical. And because this and this are identical, it means that this matrix here is the inverse of that one. And that's what we wanted to prove. mb tilde b is the inverse matrix of mb b tilde. Now let's look at an example for this. So here we have the basis b1, b2 with 1, 1 and minus 1, 1. So here you see it in the picture. And we have a basis c with c1 to 0, so the long vector here, and c2, 0, minus 1, this one. And we want to determine the matrix MBC for the change of basis representation from B to C. Now, from theorem 4, we know that this matrix is given by the two columns, which are the representation of B in the basis C, of B1 in the basis C, and the second column being the representation of B2 in the basis C. So what we need are these two representations here, these two vectors. And in order to do that, we must express B1 and B2 as linear combinations of the vectors from the other bases of C1 and C2. And we already learned in the previous chapters how to do this. We need to solve a linear system for each of these two vectors, B1, B2. So that means we have a matrix whose columns are C1 and C2. And on the right-hand side, we have B1. And the solution that we would get from this linear system would be the coefficients of a linear combination that expresses B1 as a linear combination of C1 and C2. And in the same way, we can write a linear equation system here with, again, C1, C2 on the left-hand side and the right-hand side being now B2. And here the solution would, of course, be the coefficients for a linear combination that expresses B2 in C1 and C2. Now what we see is that both of these systems have the same right-hand side. So both of these two systems have C1, C2 as the columns on the right-hand side. So that means we can solve them simultaneously. And we write the combined system as this. So C1, C2 on the left-hand side, and both right-hand side B1, B2 will be written on the at the same time in a matrix on the right-hand side. And yeah, by a mild abuse of notation, I'd simply write this as CB. And once more, I cheekily use the same letter to denote a basis, C and B in this case, and the matrix that contains these basis vectors as columns. And now we can solve this combined system, CB. So what we do first, we divide by 1/2. Then we divide the second row by -1 or multiply by -1, and we're done. So this is a very easy to solve system. And now for each of the two simultaneously solved equations, so for each column here, we can read off the linear combinations. So the solution here, 1/2 - 1 means that B1 is the linear combination 1/2 times C1 minus C2. And the second column here, -1/2 - 1, means that B2, so the right-hand side B2, is -1/2 times C1 minus C2. And you can easily verify that. I mean, you're given the values for C1, C2, so you can plug these in to verify that these are in fact true. So now the change of basis matrix from basis B to basis C is just the one, yeah, it's just what appears on the right-hand side here, because for both B1 and B2, we have the coefficients for the linear combinations here. So we just, once we're done solving this combined system of equations, we can just read off the change of basis matrix here. So MBC is the matrix 1/2 - 1 minus 1/2 - 1. Now you have an opportunity to do all of this yourself, so please pause the video for a few minutes and solve the following problems. First, like this video and subscribe to my channel. If you pause the video anyway, you will have a second to do that. And second, we're given the bases B and C with the vectors -1, 1 and 0, 1, 0, -1 in B, and 2, 1 and 1, 1 in C. And compute the change of basis matrix for these two bases, namely the one from the basis representation B to the basis representation C. So I hope you gave that a try. And for the solution, recall that the change of basis matrix MBC is the matrix with columns row CB1 and row CB2. That is B1 and B2 being expressed as linear combinations of C1 and C2, and those coefficients written in a vector. And to obtain these two representations, we need to find out how we can write B1 and B2 as linear combinations of C1 and C2. To do this, we solve the combined linear system where we write the basis vectors c1, c2 on the left-hand side and b1, b2 on the right-hand side, which is this one. And yeah, I've written out the steps here. You can think what happens. So first we divide the first row by 2. And then we subtract the first row from the second one. And then we multiply the last row by 2, and actually we subtract the last row from the first one, and then we multiply it by 2, and this is what we end up with. So that means the change of basis matrix is given by the matrix MBC with entries -2, 3, 1, -2, because these are the linear coefficients we need in a linear combination to express B1 as C1, C2. So that means -2 C1 plus 3 times C2 will give us B1, and 1 times C1 -2 times C2 will give us B2. And you can check that this is in fact true. Now, let's look at one important special case. So if one of the bases involved is the canonical basis, S, with the canonical basis vectors E1, E2, then the change of basis from any arbitrary basis B to the canonical basis is performed by the matrix MBS, which has just B1 and B2 as their columns. So in this case, we don't have to compute anything to establish this matrix. We can just take the basis vectors B1, B2 and write them as column in the matrix. That's very convenient. And so the inverse change of basis from S to B, so from the canonical basis into the basis B, is just, as we know, given by the inverse matrix. So in this case, we just take the matrix with columns B1, B2 and compute the inverse. That's important to remember because in this situation it's very easy to write down the change of basis. And also in the converse direction we can just write down this matrix and take the inverse. Recall that we briefly talked about affine transformations in chapter 2. That is a combination of a linear transformation with a translation by a fixed vector. And now we want to see how changes of coordinates work with these affine transformations. So, as I said in the beginning, a change of basis is a linear change of coordinates, but the coordinate systems between which we change are centered at the origin, so they both have the same point in space as their coordinate center. Now, in practical applications, the choice of a point as origin, so the zero vector in other words, is arbitrary. There's no naturally given origin. You just choose some point as your coordinate origin that seems convenient for the problem that you're studying. And there may be different legitimate choices where you place the origin in your problem, and because of that we might have to transform between coordinate systems that have different points in space as origins. And these are affine coordinate changes where we combine a linear change of basis and a translation between different coordinate origins. And as a brief reminder, we have seen an application of this principle before in chapter 2, section 7, and to be precise in time 4940, where we modeled a rotation about a point V that is not the origin. So we had some arbitrary point in the plane and we wanted to rotate the plane around that point. And we knew how to do rotations about the origin. Those could be easily expressed by matrices. But it got a bit more complicated when we wanted to do it about some arbitrary point that's not the origin. And I briefly recall that example here, but if you don't remember, be sure to rewatch it. Now, this was the image that summarized the whole thing. We start out with this gray figure, and this is the one we want to rotate about the point V, so that we end up with this violet figure here. Now, in order to do that, what we did is we translated the figure back to the origin. So we translated it by minus V to the origin. Then we applied the linear rotation about the origin, and then we translated it back to its original center point V. And that way we got the rotated figure about the figure that was rotated about the point V. And this can be interpreted as changing our coordinate system from our original coordinate system centered at 0 to a new coordinate system centered at V. But in that new coordinate system, of course, the point V, the vector V, would be expressed as the 0 vector. That's why we subtract V from everything. And then in this new coordinate system, we apply the linear rotation, and then we make another change of coordinate system back to the original one that we started in. And as a bit of practical motivation, let's see where something like that could come up. So in computer graphics, for example, affine changes of coordinates are often used. And here I have a screenshot of the game Asteroids, a classic. And here we have our little spaceship, it's maybe a bit hard to see, that can move freely about the screen. And now let's assume the developer placed a coordinate system in the center to compute the position of the spaceship or the asteroids or anything else that's flying around here. So for example here, these white axes might be the coordinate system the developer chose, and then here the vector x pointing to the spaceship would give the coordinates of it. And eventually these coordinates will have to be used to tell the computer how to fill the pixels on the screen, in which color, to actually draw this image here. However, graphics processors usually use a coordinate system that begins in the upper left corner of the screen. So the coordinate 0, 0 point is here. And the first coordinate grows to the right. And the second coordinate grows downwards. And in this graphics processor coordinate system, this arrow here, this vector x prime here, would indicate the position of the spaceship. So we need some way to transform from the developer's coordinate system to the graphic processor's coordinate system in order to know which pixels we need to fill. Let's make precise what we mean by all this. An affine coordinate system is a basis B with two vectors together with a displacement vector V. And this we interpret as the origin of the other coordinate system. So we write this as B semicolon V. So the pair consisting of this basis and the displacement vector. Okay, so in the picture here we have our basis vectors, and this vector V, the third one, indicates where our new coordinate system should be centered. And of course, geometrically, we think of it as taking V as the coordinate origin and then attaching the basis vectors to this new coordinate origin. And if we want to give coordinates in this new affine coordinate system, we don't start at 0, but we start at V and measure how many steps, how many multiples of B1 or B2 we need to combine in order to get to a point in space starting at V. And so we can define the affine coordinates of a point x in the plane in the coordinate system BV as follows. I call this alpha index BV of x, and this is rho bx minus rho BV. So That means first we express everything in the basis b, so we first do the linear change of coordinates, and then we translate by minus v. So especially important to notice is that in these coordinates, the point v becomes the new origin, because if we plug in v here, we get rho b of v minus rho bv, so we get 0. Okay, and this way we can pretend that v is the new origin of our coordinate system. Now let's see this for some vector x in the plane. If we pretend that v is our new origin, and here we have a vector x, so the black arrow indicates how we see it in the canonical coordinate system that we had before. But in the affine coordinate system BV, we actually want to see x as this vector here. And we can write this as, well, we go minus once in direction b1, so here, and then we go 2 steps in direction b2. So we take vector b2 and add it twice to this, and then we arrive at this point. And the combination here is this vector, which describes the point x in this affine coordinate system. You see that's of course different to this arrow here, which describes it in the canonical coordinate system. And in fact, this vector here, written out in our original canonical coordinate system, is just this arrow here. And this is exactly what we get if we translate everything by minus v. Okay? So alpha bv of x is this vector. And yeah, if we translate it by v, then it points exactly to our point x. And that's the same as just taking x minus v. So the difference here, x minus v, is that point here. And that's expressed in the basis b, so expressed by these 2 vectors, but then centered at 0 again, and this gives us alpha bv of x. Now, how do we compute affine changes of coordinates? So suppose we're given an affine coordinate system, BV, and an affine change of coordinates to or from our canonical basis representation comprises the 2 following problems. First, the change into this affine coordinate system. So we're given x, and we want to determine alpha bv of x. Or the converse change of coordinates, if we know what x is represented as in this affine coordinate system, we want to know which vector x it was originally. So given alpha bv of x, determine x. And we let, again, S, E1, E2 denote our canonical basis, and then these 2 problems here can be solved as follows. Recall from what we just thought about before, that alpha bv of x is rho b of x minus v. And rho b, as we learned earlier in this video, is computed via the change of basis matrix MSB. So if we're given x, then we compute alpha bv of x simply by multiplying MSB with x minus v, because rho b of x minus v is just MSB multiplied by x minus v. This is the matrix representing this change of basis, or this basis representation. And the main difficulty here is simply computing this change of basis matrix, but recall, since this is the canonical basis, what we do is we simply take the basis vectors b1, b2, write them as column in a matrix, and take the inverse of that. Then we obtain this matrix, and we can just multiply this by x minus v. And the vectors b1, b2, and v are of course given since we know this affine coordinate system bv. So that solves the first problem. And now for the inverse affine change of coordinates. If we're given alpha bv of x, so we know what the vector is represented as in this affine coordinate system, then the inverse change is simply given by solving this equation for x. And we can do this by inverting this matrix and multiplying by the inverse. So we get MSB inverse times alpha bvx. And then we have only x minus v on the right hand side, and we add plus v here. And we're left with x on one side and this expression here on the other side. And of course we remember that the inverse of MSB is just MBS. And again, this is simple because MBS is just the matrix that contains B1, B2 as its columns. So if we're given this, we can just take this matrix where we plug in B1, B2 as columns and add the vector V to this product, and we get X. Now, to make it a bit more complicated, what do we do if we're given two affine coordinate systems, BV and CW? And we want to transform the representation from one of them into the other. Well, then we can use the method we just developed before to transform alpha BVX into alpha CWX and vice versa. And we'll simply do this by taking a detour via the canonical coordinate system. So using what we just learned before, first we compute x from the given alpha bv of x by this formula. So x is mbs times alpha bvx plus v. And again, recall this is just a matrix with the vectors of b as columns. And once we have x, we can compute alpha CWX, again by what we learned before, as alpha CWX equal to MSC times x minus w. We can summarize this to get a really complicated formula. So alpha CW of x is MSC times x minus w, but now for x we plug in this expression here. So MSC times MBS times alpha BV of x plus v minus w. Now, to simplify this expression further, we can multiply the expression within the parentheses by the matrix MSC. And what happens then? So first we multiply the change of basis matrix MBS by MSC, but when we multiply them, we just have the combination of the change of basis from B to S and then from S to C, which just amounts to changing basis from B to C. So the product of these two matrices is just MBC. So we get MBC times alpha BV of x. And now what happens with those two when we multiply them by MSC? This is V and W expressed in the canonical basis, so in the basis S. So we can think of this V as being V expressed in the basis B multiplied by MBS. That would be a more complicated way of writing this. And then, yeah, this would also be an expression which has MBS as a factor before it. It would be MBS times rho BV. And this MBS, the same matrix as here, multiplied by MSC will also give MBC. So we can write those two as MBC times alpha BV of x plus rho B of V in parentheses. And finally, minus W multiplied by MSC is just W expressed in the basis C, so that's minus rho CW. Now this already looks complicated, but let's write it even more abstractly in a notation that is independent of the particular vector x. And we can express the affine change of coordinates, which I denote by A, BV, CW, as follows. So A, BV, CW is given by a translation. So T denotes the translation map. The translation by minus rho CW composed with a change of basis, the linear change of basis from B to C, composed with the translation by rho BV. This is a bit sloppy because, of course, here I use the notation for composition of maps, but I write a matrix here, but this is just making it shorthand for the linear transformation that is expressed by this matrix here, and I did not want to make the notation even more complicated, so you know what is meant here, and we can thus interpret an affine change of coordinate as a composition of a translation by a linear map and another translation. And we can also write this in extended coordinates. So if you recall, in chapter 2, section 8, we introduced the extended coordinate notation to use for affine transformation. So we could write this as a 3x3 matrix multiplications, where we express the translation also as 3x3 matrices, even though they're not linear. So we cannot express them as 2x2 matrices, but as 3x3 matrices in extended coordinates. But I'm not getting into this anymore here. Instead, we want to see how this works in an example and then be done with it. So suppose we're given two affine coordinate systems, BV and CW, with the following basis vectors, B being 1, 1 and minus 1, 1, and V being 2, 1, and the second coordinate system with basis C being 2, 0, 0, minus 1, and W being minus 3, 2. So here you can see this geometrically. So this is our first affine coordinate system, and this is our second affine coordinate system. Now, suppose we're given some vector x, this one here, located at this point, given in the first coordinate system. So alpha BV of x being minus 1, 1. So that is this point here. So this means, recall minus 1, 1, we take minus 1's the first basis vector and subtract it, or add it, well, add minus it to the origin here. And then we take once the second basis vector b2 and add it, and this is where we end up. So this arrow here is the vector that describes the point here in our first coordinate system. And what we want is to get the arrow from W to this point and what the coordinates of that arrow are. That means we want to find alpha CW of x. Now, remember the steps we needed to do this. So first we want to compute the vector x in the canonical basis representation. So this being our coordinate system BV. And we are given alpha BV of x to be minus 1, 1. And as we saw before, this is the following. X is MBS times alpha BV of x plus V. So we have everything here to compute this. We take the matrix MBS, which is just the matrix which has B1 and B2 as columns, multiplied by alpha BV of x, which is this one. And then we add V, which is this vector here. Now, this matrix written out is this, as we can see from here, and what we get is 0, 1. So this point here is the vector 0, 1, expressed in the canonical coordinate system, and that was just the point with coordinates minus 1, 1 in our first coordinate system. And now we want to take this and express it in the second coordinate system. So we know x, and we can now compute alpha CW of x. And as we saw before, this is MSC times x minus w. So we can plug in x and we can plug in w since they are known. So we get MSC times 3 minus 1. Now, to finish this, we must get MSC, and we know this is the matrix because here we have the canonical basis involved. And we write the columns C1, C2, and then take the inverse of that matrix. And here, in this case, it's really easy to compute because we only have the two diagonal entries in the matrix, 2 and minus 1, and we can just take the inverses of those to get the inverse matrix MSC. And if it was a more complicated matrix here, then you would just use Gauss elimination, or also called roll reduction, that we learned in chapter 4, or chapter 3 it was actually, and compute the inverse. So what we get is, once we computed this matrix here, we multiply this by this vector. So alpha CW of x is this matrix by this vector, which is 3/2, 1. And that is just this vector here. So what does it mean? This point here is expressed by taking 3/2 times the first basis vector plus 1 times the second basis vector, and add this to the origin w, and then we'll arrive at this point. And we can check this geometrically. So this is C1, and if we go into this direction of C1 and add another half length of C1, so that would be this bit that we add here, and then we go down precisely once the length of the vector C2, then we arrive at this point here. And yeah, that's the vector connecting these 2 points is this one here, which is precisely 3/2, 2. And that's all I want to say about affine changes of coordinates. From now on I will stick to changes of basis, that is linear changes of coordinates. And recall that we express linear maps by matrices that contain the images of the canonical basis vectors as columns. And we can also express linear maps in coordinates relative to other bases. And for that we want to compute changes of basis for linear maps. Now, in chapter 2 we learned that for any linear map phi we could assign a matrix such that phi x is equal to ax. And yeah, the columns, as I just said, the columns of A are just phi e1, phi e2, where e1 and e2 are the canonical basis vectors. And also recall from chapter 2 that for some linear maps, for example, we had reflections as one of these, the matrices are easy to find if we reflect across certain special axes, like the e1 or e2 axis. In that case, we had these two matrices, A, E1, the reflection across the E1 axis is just 1 minus 1, which means the first coordinate is kept and the second coordinate is just flipped. And for the reflection across the E2 axis, we have AE2, the matrix with diagonal entries minus 1, 1, where the first entry of a vector is flipped and the second entry is just fixed. But we also saw that for reflections across an arbitrary axis L at some angle alpha with the E1 axis, it was much more difficult to express this by matrices. And in this case, what we did is we first rotated this axis L by an angle minus alpha onto the E1 axis. And then we used this reflection matrix to perform the reflection and then rotated back the E1 axis to its original position onto the original axis L. And that meant rotating by an angle plus alpha. So it turned out in chapter 2 that the reflection across the axis L has the matrix AL, which is, well, first rotation by minus alpha, then the easy reflection AE1, and then rotation back by plus alpha. And as we know now, the rotation by minus alpha is the same as the inverse of the rotation by alpha. And what really happened here is that we actually did a change of basis. So by applying the rotation r minus alpha, we changed our basis from the canonical basis to a basis b1, b2, whose first vector b1 points in the direction of the axis L. And the second vector b2 is perpendicular to b1, just like in the canonical basis e2 is perpendicular to e1. And then the reflection we want to perform is expressed in this new coordinate system, in this new basis, by the simple matrix AE1, because now in this coordinate system L corresponds to the E1 axis. So after we performed this reflection, we change the basis back to the original canonical basis via the inverse rotation R alpha. And in this way we obtain the matrix for the reflection across L in the canonical coordinates. Now the moral to be learned here is that we can simplify computational problems by changing to a different coordinate system. That's actually something very important to remember, because you will use this a lot in mathematics. So how do we compute the matrix that represents a given linear map phi in an arbitrary basis B? So phi of x is given by the matrix A, so phi of x is A times x. And let's say that MSB is the change of basis matrix from the canonical basis S to the basis B. Then we have the following. Phi of x represented in the basis B, so rho B of phi x, is, because of this, the same as rho B of AX. And this is the same as MSB times AX, because this here we can view as rho S of AX, so the canonical basis representation of AX. And we change from this canonical basis representation to the basis representation for B, and this is done by MSB. So to get this, we multiply AX by MSB. And now what we can do is we can view just the vector x as being represented in the canonical basis, so rho S of x is equal to x. But we can view this as the change of basis from B to S of rho B of x. So assume we were given x in the basis B, then we could multiply this by MBS to get x. So we can replace x by this expression here. So what we find is in the basis B, rho B of phi x is the vector rho B of x multiplied on the left by the matrix MSB times A times MBS. And you see from the order of the indices here, it's like coming in with a representation B, changing it to the representation S, performing the operation, and then changing back from S to B, and come out in the basis B with the result of our operation. And we call this matrix here rho BB of phi. So rho BB of phi of the linear map phi is MSB times A times MBS, where A is the matrix representing phi in the canonical basis. And recall that this is the inverse of this one, so we could write this as MBS inverse times A times MBS. And yeah, we call this the representation matrix of phi in the basis B. Note here the row has two indices, because this linear map takes once the basis representation B as an input and spits out again something represented in the basis B. So here the notation for linear maps differs from the notation rho B for vectors, because here we have an input and an output for a linear map, and here it's just applied to one vector. Now, clearly the matrix A here is just the representation matrix of phi in the canonical basis, so we could write this as rho SS of phi. And in the basis B, we have rho B of B1 to be 1, 0, and rho B of B2 to be 0, 1. So if we use this, we find that rho B of phi B1 is rho BB of phi, the matrix of phi represented in the basis B, multiplied by rho B of B1, so the vector B1 represented in the basis B, but that's just E1, the first canonical basis vector. And similarly, rho B of phi of B2 is just the matrix rho BB phi multiplied by the second canonical basis vector, E2. So multiplying a matrix by this vector gives the first column of that matrix, and multiplying a matrix by this vector gives the second column of this matrix. So these here, rho B of phi B1 and rho B of phi B2, are just the first and second column of this matrix rho BB of phi. So if we have some problem where the information we are given are the images of B1 and B2 under this linear map phi, and we have this represented in the basis B, then we can easily write down this representation matrix rho BB of phi by simply taking these two vectors here and writing them as columns in this matrix. And we want to study this in an example, but first we look at it geometrically. So recall what I said about the reflections across an arbitrary axis. So here we have the axis L that we want to reflect about. So if we have a vector x, then we just reflect it about L, and this sigma Lx, sigma being the reflection across this axis, maps it to here, and similar for any other point. So a point here would be reflected here, point here would be reflected somewhere over here, and so on. And alpha is the angle between the E1 axis and the axis L. So this was the case where the matrix to describe this linear map sigma L is not obvious in the canonical basis. And what we do is we change to a basis B consisting of these two vectors. So B1 is just the rotation of E1 by the angle alpha, and the same way B2 is just the rotation of E2 by the angle alpha. Okay, so B1 and B2 are just the same length as E1 and E2, and they are just as those two, they are perpendicular to each other. And now we want to express the problem in this coordinate system. But in this new coordinate system, B1, B2, the reflection across L is just negating of the second coordinate, because as you see, if we reflect across L anything on L, so any multiple of B1 is just mapped to itself, because nothing happens to these points on the red line. And if we decompose any point x into a linear combination of B1 and B2, so like this, then it means what happens is we keep the coordinate in this direction, so parallel to the axis, and we flip the coordinate perpendicular to it. So we take the B1 coordinate and take the negative of it to get to the reflected point here. And so we see in the new coordinate system, it's actually very simple to express what happens with this reflection. One coordinate stays fixed and one coordinate gets flipped. Now, let's work this out algebraically to make it more precise. We have the basis b1, b2 that arises from the canonical basis by rotation with an angle minus alpha. So MSB, the change of basis, is rotation by minus alpha, which, if you recall from chapter 2, is just this matrix. And its inverse, for the inverse change of basis, MBS, this is just rotation by plus alpha, so that's this matrix. It's just the minus sign in the sign expressions are exchanged. Now, in the basis B, the vectors b1, b2 are represented, as we saw before, by the first and second canonical basis vector. So the reflection, sigma L, maps rho b, b1 to itself and rho b, b2 to minus rho b, b2. Okay, so this is mapped to itself because it lies on the reflection axis, so nothing happens to it. And here we just flip the coordinate. So the matrix that represents this reflection in the basis B, rho BB of sigma L, is just 1, 0, 0, minus 1, which we previously called AE1. So this is the same matrix as the reflection across the E1 axis in the canonical basis. Now we want to find the matrix for sigma L in the canonical basis, which we called AL. So we can write this more fancily as rho SS of sigma L. And by what we learned before, this is the same as applying the change of basis MBS to rho BB of sigma L, and then applying the change of basis MSB. And we know all these parts. These are the two rotation matrices, so MBS here, MSB here, and this is the matrix here. So this is in fact the same as R alpha times AE1 times R minus alpha, and that is what we derived before from a different point of view, where we thought about rotating the axis rather than changing the coordinate system. But it's just two different points of views on the same thing. Now we change the basis representation between two different bases. So suppose we're given two bases B and C. Then we can use the change of basis matrix MBC to transform the representation matrix rho BB of phi into the representation matrix rho CC of phi for any linear map. Now we know that to get from the representation in the basis B to the representation in C, we multiply a vector by MBC. So if we want to have rho C of phi of x, that's the same as taking rho B of phi of x multiplied by MBC. And this, again, we can express as follows, as rho BB of phi applied to rho BB of x. And so what we get then is MBC times rho BB of phi, and we can replace this by MCB times rho CX. So we plug in representation of x in C and get out representation of phi x in C, and we take the detour for the computation via the basis B. So we transform x in the basis C to the representation in B, then apply phi represented in the basis B, and then transform back the result of that, we transform back into the basis C. Also, we have that rho C of phi of x is rho CC of phi times rho C of x, and comparing this equation and that equation, we find that rho CC of phi is this matrix here, so MBC times rho BB of phi times MCB, and again recall this is just the inverse of that one, so rho C of phi is in fact inverse of MCB times rho BB of phi times MCB. And more precisely, this equality follows because the matrix on the left and the matrix on the right take the same value when multiplied with vectors of a basis. So if they coincide on a basis, then the matrices here and here must coincide overall. And we can crank up the generality even more. So suppose now we're given two bases, B1 and B2, and a linear map phi of x equal to A of x, then we define the representation matrix rho B1, B2 of phi in the bases B1 and 2 to be rho B1, B2 of phi is ms B2 times A times ms B1. So this matrix we use if we get as an input a vector represented in basis B1, but as an output want to have a vector represented in basis B2. And if we're given four bases, B1, B2, C1, C2, then the change of basis for the representation matrices is done as follows. So we want to have row C1, C2 of phi, but suppose we're given this one here, row B1, B2 of phi, then we can get this by multiplying mB2, C2 times row B1, B2 of phi times mC1, B1. And the computation to prove this is similar to the ones before. So if you want, you can do that as an exercise. Also note again what I said about the indices before. Whenever you have an expression where two factors next to each other have one index in the upper and one in the lower index, then these indices disappear in the end result. You can see that beautifully here. B1 and B2 appear each as a lower and upper index next to each other, so they disappear, and the only thing we're left with are C2 and C1. Now, we rarely are interested in such representations with different bases in two-dimensional linear algebra, but they can be relevant in higher dimensional linear algebra, especially when we're dealing with non-square matrices, so when we're looking at linear maps between vector spaces of different dimensions. But for now, we just notice that such things exist, but we will not really use this a lot. Now, one last piece of ideas and vocabulary to conclude this chapter, because it's important for any future endeavors in mathematics you might take. So we know that change of basis matrices are invertible, but conversely we can take any invertible matrix A with columns A1, A2, say, and interpret this as a change of basis. For example, this can be the change of basis from the basis with vectors A1, A2 to the canonical basis. Now, if we are given any matrix X, then we interpret the matrix vector product of X by any vector in the plane as a geometric operation, then we can compute A inverse times X times A. And this is the same geometric operation, but expressed in a different basis, namely the basis given by the columns of A. And we call A inverse X times A the conjugate of X by the matrix A. And two matrices X and Y that arise in this way as conjugates of one another by some matrix A are called similar, or sometimes also are called equivalent. And it's reasonable to expect that X and its conjugates share many properties because they describe, as I said, the same geometric operations. So if they describe the same geometric operation but just in different coordinate systems, then there should be properties that are intrinsic to this geometric operations that are not relevant, or where the basis representation is not relevant. So they should be shared between X and all of its conjugate matrices. And no matter which conjugate it is, so if we use different matrices A to conjugate X, then these properties should be preserved. And this is something we will observe repeatedly throughout our studies. And that's always an indicator when you have a property of a matrix that is preserved under conjugation, then this is like an invariant a geometric invariant property, so it does not depend on the choice of your coordinate system. It is intrinsic to the geometric operation that is described. And yeah, as I said, we will see some of that behavior throughout our studies and also soon in this course here. But for now, I'm at the end of this lecture. Thank you very much for watching, and please do not forget to like and subscribe.